Hey everyone, today I'll talk about a new method for computing signed distance. Signed distance functions, or SDFs, are essential for many problems across graphics, geometry processing, robotics, and vision, including a recent resurgence in popularity as a learnable representation for shapes. But how do you get high-quality SDF from messy, real-world input? Unfortunately, ordinary signed distance is not well defined as soon as the source geometry is broken, meaning it might have holes, self-intersections, noise, or other errors. We introduced the signed heat method for computing signed distance to broken geometry. As input, we take oriented curves within a surface domain or surfaces within a volume domain. As output, we get an approximation of the signed distance to the original unknown geometry without ever needing to explicitly reconstruct that curve or surface. Our algorithm applies to all discretizations in all dimensions, is robust across a wide variety of errors in the input, and generalizes signed distance to cases not previously considered by past distance algorithms. Our algorithm is simple and efficient, consisting of three basic steps. First, we diffuse the normals of the source geometry. This extends information about the geometry's orientation to the rest of the domain. Next, we normalize these diffuse vectors, yielding a unit vector field that approximates the gradient of an SDF. And finally, we find the function whose gradient best matches this unit vector field, obtaining our generalized signed distance function. Later, I'll explain why this procedure converges to the true signed distance function. The signed heat method builds on past heat methods in geometry processing. In particular, the unsigned heat method diffuses a scalar heat distribution to recover geodesic distance. However, their method is limited to unsigned distance only. Next, the vector heat method starts out by diffusing a vector value distribution like ours. However, the vector heat method doesn't compute signed distance. And although there's been some past exploration of robust signed distance, there's still no go-to method that computes reliable signed distance in the general case. There are also many algorithms for unsigned distance, but these don't help find SDFs to broken geometry. Even if you had the exact unsigned distance, simply signing it doesn't make sense. So what do we do instead? Our algorithm starts by considering parallel transport along shortest paths, or geodesics. In the plane, parallel transport of a vector along the shortest geodesic connecting two points P and Q simply amounts to the translation of the initial vector along the straight line connecting the 2 points. On a curved surface, we can also consider the shortest geodesic connecting 2 points, and similarly ask that this vector turn as little as possible as it travels along this curve, keeping the angle between the vector and the curve's tangent as constant as possible. Amazingly, parallel transport along shortest geodesics can be computed using vector diffusion. We aren't the first to make use of this fact in geometry processing, but we are the first to recognize the following implications for computing signed distance. Our first key insight is that the theorem tells us that as the diffusion time becomes shorter and shorter, a diffused normal vector will align with a vector obtained by parallel transporting the normal along a minimal geodesic, which means that this vector aligns with the gradient of distance, since parallel transport preserves the vector's tangency along the geodesic, and because traveling along the shortest geodesic is by definition the shortest way back to the source geometry. And because we transported oriented normal vectors, we get the correct sign, so we conclude that diffused normals will be aligned with the gradient of signed distance. Our second insight is that we can now normalize and integrate these vectors to obtain signed distance, because although the vector's magnitude will decay away from the geometry, we previously established that diffused vectors will at least have the correct direction, so to obtain a distance gradient which has unit magnitude everywhere, we can simply normalize. And once we've obtained an approximation of the gradient of signed distance by normalizing, we can simply integrate to obtain the signed distance function itself. So to summarize, our key insights are the following. 1. For small diffusion time, diffused normals will be parallel to the gradient of signed distance. And 2. Because we know these diffused normals point in the same direction as the gradients, we can normalize and integrate these vectors to recover an accurate SDF. These insights lead directly to our algorithm. As a first step, we integrate the vector heat equation for a short time, which diffuses the normal vectors. Then we normalize the resulting vector field to have unit magnitude everywhere. Finally, we look for the function whose gradient is as close as possible in a least square sense to the normalized vector field, and the minimizer satisfies the following Poisson equation. Translating this algorithm into the discrete setting is straightforward. As in past heat methods, we discretize the vector heat equation in time using one step of the backward Euler method. This yields the following linear system, which we solve for a single fixed time t, and we set this time to be equal to the mean distance between nodes in our mesh. Then we discretize this equation in space. On triangle meshes, we use basis functions associated with edges, which makes it straightforward to encode normal vectors. Then we normalize the diffused vector fields onto faces, and using basis functions at vertices, we discretize the final Poisson equation using standard techniques. In total, our method amounts to solving just two sparse linear systems. Beyond triangle meshes, our method applies to virtually any data structure in any dimension. And not only can we compute signed distance to curves, but we can also compute unsigned distance to isolated point sources in open curves and even combinations of all types of distance. Through careful treatment of boundary conditions, our method also displays correct behavior at the domain boundary. Contrast this to the unsigned heat method, whose distance fields can be incredibly warped near the domain boundary. For more results, here we compute generalized signed distance to a broken surface where the ambient 3D space has been discretized using a TEP mesh. By extracting level sets, we can convert broken input geometry into closed manifold surfaces. And we can obtain evenly spaced offset surfaces. Our method can also be discretized onto grids. You can also generalize morphological operations using our method. Here we take negative and then positive offsets of generalized signed distance functions, which simplifies high-frequency features of broken shapes as if they were whole. In general, we find that our method is robust to defects in the source geometry, for example, ones that might arise from drawing on surfaces. More generally, our method is robust to a variety of errors in the source geometry, including topological errors such as broken curves, geometric errors such as noise, and orientation errors where the source geometry is inconsistently oriented. Our results degrade gracefully in the presence of progressively worse input and maintain small qualitative and quantitative error relative to the ground truth solution. Our method is also robust to errors in the domain itself and applies out of the box to non-manifold and self-intersecting meshes. Likewise, our method applies directly on non-orientable meshes like Mobius bands. Now I'll discuss some optional extensions that give our method even more generality. One extension is better preserving level sets. To better align level sets with the source geometry, we can simply introduce a constraint that the distance be constant along the source curves. This constraint is linear, and the optimization can be solved with another sparse linear system, and we can impose this constraint without needing to know the ISO values before solving. By applying this constraint to each connected component of a curve, for example, we can better match an SDF to several partial level sets simultaneously. Our method also generalizes signed distance to non-bounding curves, which fundamentally have no inside or outside. In these cases, the gradient of signed distance may only be able to be integrated with a piecewise continuous function, so standard integration will yield distorted isolines. We could just filter out non-bounding components of the curve, but instead we'll again consider a generalized notion of signed distance that remains meaningful. In particular, we can replace the L2 integration problem we had before with one that allows discontinuity where the vector field is highly non-integrable. The optimization corresponds to a sparse linear program, and solving this L1 problem, we can obtain a piecewise SDF with well-behaved isolines despite the inherent sign ambiguity. As another extension, one can optionally sharpen our SDFs, using a formulation of distance as a convex optimization. By itself, this formulation can only compute unsigned distance, but with our method, one can first compute a generalized SDF, then make a simple change to the convex objective to sharpen cusps and distance accuracy while preserving the inside-outside computed by our method. Finally, because our method is based purely on PDEs, we can discretize those PDEs on a variety of spatial structures, including polygon meshes, point clouds, and voxelized surfaces. All we need is a divergence operator and Laplacian defined on the data structure, and we simply take advantage of Laplacians developed in previous work. Now we turn to evaluation, where we find that our method is competitive even to methods that only compute unsigned distance. We first considered closed planar curves, where we found that our method is comparable in performance and accuracy to other heat methods, as well as being about an order of magnitude faster than other state-of-the-art methods for unsigned distance. We also evaluated our method on a benchmark of closed curves on surface meshes. Here we plot solve times, finding the same trend as we did in the planar case. We also observed that our method has approximately linear convergence with respect to mesh refinement and has better consistency on curve sources compared to other methods. Finally, we compare against the end-to-end pipeline of repairing broken geometry using winding numbers, then computing the distance to the fixed geometry. Overall, we found that our method is better at classifying inside and outside, and as a result yields more accurate SDFs. We further examined this behavior on 220 examples and found that winding numbers misclassifies the majority of the domain in 12% of examples, and the results aren't much different using a different contouring method. As a consequence, the repair then compute distance pipeline yields about 3 times lower distance accuracy on average, in addition to being about 10 times more expensive because of all its intermediate steps. We find this robustness of reconstruction especially compelling in 3D. Winding numbers and Poisson surface reconstruction fill in holes with flat or saddle-like patches, independent of the observed surface, and the behavior doesn't get better no matter which level set we take. In contrast, because we diffuse normal vectors, we obtain more faithful surface reconstruction that more closely aligns with the curvature of the surrounding surfaces. In conclusion, the signed heat method is an efficient, robust, and broadly applicable algorithm for computing generalized signed distance. Algorithmically, our method is incredibly simple, amounting to just 2 sparse linear systems. And yet the generalized signed distance functions we obtain are robust to a spectrum of errors in both the source geometry and the domain. We compute these generalized SDFs on both 2D surface domains and 3D volumetric domains, and find that our method obtains better surface reconstruction results than computationally similar algorithms. While I think there's even more to be explored regarding surface reconstruction, another fun future direction could be diffusing line fields from source geometry without any orientation. Recovering orientation from completely unoriented input has long been a challenge to this class of algorithms, and it remains an open question if we can then simultaneously obtain both distance and orientation. Recently, there's been a lot of interest in orienting geometry, including some new work just presented in this very session, and it would be interesting to see if we could extend these insights to also recover distance. Thanks!